Hello everyone, and welcome to this video titled The Limit of a Function. So in this video, I'm going to be taking you through a preview version of a Knewton Alta assignment that is titled also The Limit of a Function. So please understand that this is a preview of the assignment, and so questions I'll be working on in this video may not be exactly the same as the questions that you work on as a student, if you're working on this assignment yourself. But the objectives are the same, and the way I would go about doing certain problems is the same as what you'll be doing. So hopefully watching me go through this will help you when you do it yourself. So here we are, Knewton Alta's site, and you won't see the word preview, you'll just see the title. All right, so in this particular course, the limit of a function is section 2.2. Upper right hand corner, you have your mastery bar, which shows you how far along you've gotten in the assignment. The activity log next to this, you click on that, it'll show you all the objectives. So this one has 6 objectives broken up into 3 parts. So we're going to be in the intuitive definition of a limit until those 2 are done, and then it'll move me to one of the other 2 sections until they're done, and then the last section until those 2 are done. So we're going to be doing pretty much 2 objectives at a time. And you can see how far along you've gotten on each objective with the progress wheel next to it. So you should also on the home page here see the current objective for the question we're working on, then the question itself. Now you can switch sections if you wish. Instead of working on one section with these 2 objectives, I can hit switch and go and start another part of the assignment if I wished. But I'm not going to be doing that. Then a question related to the current objective below it. And at the very bottom of every question, you should see a feedback button. This allows you to send feedback directly to Knewton's support. So you see a typographical error in the question, in the answers, the solutions. Please send them feedback, and their team is usually pretty good at fixing things, helping you out. I hope it's obvious that you will not have, as a student, the instructor cheat button. It's just for instructors and demonstration purposes only. But you will have a more instruction button. So if you're working on an objective or a question and you forget how to do it, forget the material, or need to brush up, click on more instruction, and some reading, maybe some videos, maybe both, will come up that will instruct you on the objective you're currently working on, and hopefully with that instruction you can do the problems better. Okay, so this first objective is evaluate limits graphically. All right. So first, let me talk about some of the notation here when it comes to limits and how to interpret it graphically. All right, so limits, the notation you're going to be coming across quite often is this LIM for limit, and then below that you'll have some variable. It's not always x, but in my initial notation here I'll have as x approaches, little arrow, and then some value called a. And then after this limit notation is some expression that depends on this variable. So if I have x, approaching a in this line here. The function, the expression I'm looking at, will be a expression depending on that x, that has x involved. Now, when we have this notation, we're going to say that this limit approaches some value called L. I'll use capital L for the word limit. So what this all means, if I'm saying this means that as x, right, so the value of x approaches, gets closer to x equals a, but not x equals a, right? So we're going to get closer and closer to this a value, but not actually plug in the value of a initially here. So as x gets nearer and nearer to this a value, f of x, the value of the expression, the value of that expression f of x gets closer to, or approaches L, and it can be equal to L as well. So that can't be a, right? This is implying here that x is not a, whereas when the limit they say is L, it can be equal to L, but so you're getting closer to L, but it could also be L itself. So graphically, right, which this objective is about, that means the following. So here's the xy plane, and this statement up here is about a value called x, at x equals a. So here's a on the x-axis, and if the value, the y, over here is a y value, you can think of this as an output or a y value. So, what this all is saying is that as x gets closer and closer to a, as I plug in values near a, the output of this function gets closer and closer to this L value on the y-axis. So I'm going to put an open point here. This is an empty point. It doesn't, the location doesn't have to actually be there. So there's the point, x equals a, y equals L. So what this notation means as a graph, graphically speaking, again, is that if I approach a, from the left, the graph will approach this location with a y value of L. Same thing on the right side. This is going to be referred to as a two-sided limit later. So as I get closer to a on the right side, the graph, all right, so here's the approaches this location. Here's y equals f of x. So again, from both sides of x equals a, as the x value gets closer and closer to a, our graph gets closer and closer to this location with a y value of L. All right. And this is another thing I could write here. This means that the graph of y equals f of x approaches, again, it doesn't have to hit it. That point does not have to be there, but we're getting closer and closer to it. Approaches the location, approaches the points, a comma L on the xy plane. All right, so this is a graphical interpretation of this limit statement. And if this doesn't happen, all right, so if the graph doesn't approach a specific location, a specific point like this, then they'll say the limit doesn't exist. So if the graph of y equals f of x does not approach a specific location, I'll say a single location, a single point, as x approaches a, then we will say that this limit, the limit as x approaches a of our function, does not exist. All right, now the abbreviation for this you're going to see quite often is just DNE. So some examples of cases where that's happening. Here's XY, here's A on the x-axis. So one instance where they'd say this limit does not exist is if from the left side of A you approach one location, but from the right side of A you approach a totally different location. Right. So in this case, they would say the limit, again, here's the graph of y equals, some function of x. Again, not approaching the same location on both sides. So we would say that this limit as x approaches a of our function, does not exist. Another, or there's other cases. I'm not going to put every single scenario up here, but so again, xy axis, xy plane, here's the value called a. So again, maybe you have what's called a vertical asymptote, where on one side, say on the left side, as I get nearer to a, the graph, goes up forever. Now we're going to call this an infinite limit later and actually say it's infinity on one side. But maybe on the right side, it actually approaches some location. So here's y equals f of x again. Same deal. All right, same deal. On both sides of A, the graphs are going to different places. That's all that's all you need to see to say that a limit doesn't exist. All right, so on either side, left side, right side, the graph is going to different locations, right? These are clearly going, and when you get closer and closer to x equals a. All right, so back in the problem, we're asked to use the graph of h of x shown below to evaluate the limit as x approaches 6 of h of x. And then if possible, if the limit does not exist, enter this, this will be the empty set symbol, the does not exist symbol. Okay, a little circle with the slash through it. This should be part of the keyboard. So look, we have the limit as x approaches 6 of h of x. So if you look at this picture, now I'll draw a little bit of this up, all right, on my paper, just for this first one at least. So it looks like here's what's happening. Right? So you got your XY plane. We're seeing what happens, as x approaches 6. So here's 6 on the x-axis. Now in that picture, there was this y value of -2, right? So the graph had this point on it. So now it's filled in. It doesn't have to be empty. It could be there, but again, it doesn't really matter what happens at 6. It's what happens to the left and right of 6. So here's the point, 6 comma -2. And it looks like the graph is doing this. It's coming in toward that point from the left of 6, and also coming in toward that point from the right of 6. Right? This was just part of it. It looks like that, but so because the graph is approaching the same location from both sides, the y value of that location they're approaching will be called the limit. So here's y equals h of x. So we'll say the limit as x approaches 6 of this h function is -2. So once again, this means the graph of h is approaching the location, approaching the point 6, -2 on both sides. Okay. So that's what I'm going to enter is -2 here, right? They're asking me to fill in that limit. So down here, as x approaches 6, looks like -2. Enter -2 and then submit. And hey, if you get it correct, you get a green band with some encouraging words. And also an answer explanation. Now you get the answer explanation whether you get it right or wrong. And I would recommend reading it either way. If you get it wrong, definitely read through the answer explanation and see if you can figure out where you went wrong. And hopefully you can learn from your mistake the next time you do a problem like that. But even if you get it correct, maybe glance through the explanation, see if they're doing a problem in a different way than you did it. And maybe you like the way they're doing it better, and maybe you'll try that the next time you see a similar problem. All right, so let's continue on here. All right, so it switched objectives on me, right? Again, it's going between those two and that intuitive definition of a limit part of the section. So next objective is understand the limit of a function and evaluate a limit from a table. All right. So here we have the limit as x approaches 0 of the sine of 1 divided by x squared. And it says use the following table of values. And we're saying what happens as x approaches 0. Then it says here to enter an exact answer. So no crazy decimals. All right. Enter an exact answer. If the limit does not exist, submit your answer as this empty set symbol. All right. Now this one, if you were to look at, all right, so this is a little deceiving, this one. So what I want to do, so look at the table. So you see in this table, on the left part of the table, you see how the value of x, you got -0.1, -0.01, -0.001, right? The value of x is getting closer and closer to 0, but on the negative side of 0, right, to the left of 0. And then you have your outputs, right, the value of f at x, and you get all these values here. Now, again, this is a little deceiving because of the fact that these two last values are pretty much the same. But you see how the value is kind of fluctuating. It's -0.5 to -0.3, -0.35-ish, and then 0.9, and then -0.48, and then -0.6, right? So there's no real pattern here. And in fact, it went from, -0.3449 here to +0.93, right? So it looks to me like it's fluctuating a lot. Same thing over here on this part of the table, the right half. The value of x is approaching 0, getting closer and closer to 0, without actually, becoming 0, right? You can't plug in 0 to this function. You have 1 divided by x squared. Right? So x is getting closer and closer to 0 on the right side, right? The positive side. And once again, the values of f are fluctuating quite a bit and not approaching, a specific location. So I would say this limit doesn't exist based on that, right? I know it looks like they're both approaching this negative 0.611 number, but that the whole fluctuation thing is throwing me off. Now, I know I have more experience, of course, so I know what this graph is doing near 0. Again, you're going to get this wild fluctuation near 0. And so I want to show you a graph of this function. So I'm going to Desmos here. This is desmos.com, a free online graphing calculator. Make sure you're in radian mode, right? Go to settings, make sure you're in radians when we're working with trig functions here in calculus. So that expression was, the sine, so I'm going to graph y equals the sine of, and then it was 1 over x squared. And look at this, look at what happens near 0. Look at the wild fluctuation that goes on there. So you could actually set, that you can't even see where 0 is, right? There's 0 there. Turn the graph off and then turn it back on. You see how every single value between -1 and 1, right? Because sine is, fluctuating between -1 and 1, is being approached here. Not going to get too much into it. You don't see these too often, especially after this section, but this wild fluctuation of the graph, this wild oscillation of the graph around x equals 0 tells me, hey, this graph is not approaching a specific location, right? No matter how close you zoom in, and look at how it's approaching all locations, between -1, or where y is between -1 and 1 here. So because the graph is not approaching one specific location, right? It's not approaching one specific point at 0. We'll say this limit does not exist. Okay, so I'm going to enter this circle with the slash thing, which should be in the keyboard right off, and submit. Now let's read through their explanation. Again, maybe that wasn't clear what I was saying. Now they show you how some limits, I can plug in certain values that go to 0, right? 2 over pi, 2 over 3 pi, 2 over 5 pi. All these values are getting smaller and smaller and smaller. And, the corresponding values of f are this, right? And they say, we notice, right, hopefully we is also including you. We notice that these values of f alternate sign, without again approaching a particular value. So it's reasonable to conclude that the limit does not exist, and into the little circle slash thing. And then they show you the graph here, right? The wild oscillation near 0. That's insane fluctuation. So again, from the graph, from a table here, we would surmise that the graph of this sine of 1 over x squared, right, does not approach one specific location, one specific value as x goes to 0. It's closer to 0. So I'm hoping that makes sense. Got to approach one specific location for a limit to exist. Okay. So back to evaluating limits graphically. So kind of like the problem earlier, just look at, here's this graph of, this dark blue graph here, and they're asking for, what's the limit as x approaches, -3 of this h of x function. And if it does not exist, right, so again, if you're not approaching the same location on both sides of -3, then it doesn't exist. So here's x equals -3. Hopefully my cursor is showing up there. And the point, it looks like the graph is approaching the same point on both sides of -3 and that's the point -3, 2, right? The y value of 2 is being approached on both sides. So this limit they're asking me for, I would say, is 2. And just enter that in the box here. Wonderful. Okay. All right, so back to more evaluating, you understand the limit of a function and evaluate a limit from a table. So this is just what's the notation? Can you read the notation? So remember that a value was the value x was approaching, so that would be -3 here. F of x is the expression after the lim notation. So the f of x, the function, we'd be plugging values into near x equals -3. The function we'll plug into is 3 minus 5x. So I'm putting that in this box. And then that capital L was the limit, the y value that the outputs would be approaching. So that's the 18 here, and that looks like it's all that's being asked here. So can you recognize the notation and what's what part? What's the A, the f of x, and the L? So that's really all that one's saying. They're asking you to do. And again, they go through the notation again here, and just copying, matching all the parts of it. Another graphical one. So very similar to the previous two. So this graph down here is the graph of h of x, y equals h of x, and we're asked to evaluate the limit if it exists as x approaches -3. So once again, go down here, there's -3 on the x-axis. Now look at what is, now I don't care about this point up here, right? There's this solid point with -3, 2. I don't care what happens at -3. We want to see what happens to the left and right of -3 and what location is the graph approaching. So if hopefully you're seeing my cursor, to the left of -3, we're on this part of the graph going down to this open point down here, right? -3, -6. The graph is approaching that location on the left side of -3. And then same thing, go to the graph that's to the right of -3, and you're approaching the same location. So this location, right, has a y value of -6. So that's our limit, right? The graph, as x approaches -3, the y value, the function is approaching -6. So again, like I said earlier, the point doesn't have to be there at -3, is right, but we are approaching that location on both sides. So -6 for that one. So another graphical one, another -3. Hopefully they're not all -3. I think the first one was 6, right? So once again, here's what happens, what's the limit as x approaches -3. So here's -3 on the x-axis. Once again, there's a missing point here, and that doesn't matter if it's there. What we focus on is to the left, to the right. Is the graph approaching the same location? And that's also yes here. To the left, the graph is approaching this -3, 4 point, and to the right of -3, the graph is approaching this -3, 4 point. So the limit is the y value of that point. The limit of the function at -3 here, as we approach -3, is 4. So again, this whole solid point down here at -3 doesn't matter. Right? It's what's happening to the left and to the right. Are they approaching? Is the graph approaching the same location? All right, so once you've completed an objective, you should get a notice about it, telling you how many more you got to go, right? At 1 of 6. All right, so once again, we're just filling in pieces of the notation. Not a whole lot to go on here. So it says, the limit of the function f of x is 5 to the x power as x approaches 2 is 25. So you see this x approaches 2. So after the arrow here, I'm putting in 2. X approaches 2. Then in the parentheses after the limit notation is the function we'd be plugging into. So that's this 5 to the x power. That's going to go in this box. And they're telling us this limit is 25. So that goes over here, right, what the limit is equal to. And you can probably have figured that out, right? As x approaches 2, 5 to the x power would get close to 5 to the 2 power, or 5 squared, 25, so the limit's 25. And if you were to look at the graph of the exponential function y equals 5 to the x, as x got closer to 2, the graph would be approaching the point 2 comma 25. And you can make a graph if you want. But it's just filling in, again, pieces of the notation there. And again, they just match things up. All right, so this one, once again, is just to hope, they're just trying to get you used to the notation and identify the missing pieces of the notation. So again, the a here, what x is approaching, is -3. The function that we'd be plugging into, the function we're taking the limit of, is this x squared plus 5x plus 3. So that's what I'm entering here. And then the limit L is what this is equal to, right? What's the y value that's being approached, which is also -3 here. So as x approaches -3, the y coordinate on this graph would approach -3. The graph on both sides would approach the point -3 comma -3. So this L, this limit, is also -3. So again, just filling in the pieces from the notation. Great. All right, so hey, confetti, wow. All right, so awesome. You completed 2 of 6 objectives. So we continue on. So now we're in, so if you look now, so I finished the intuitive definition of a limit part. So now we're into, now they moved us to one-sided limits. So that now I'm going to be sticking in here, unless I want to move. You can hit start on infinite limits. But I'm going to be in these one-sided limit parts for the next 7 or 8 questions. So this next objective, explain the relationship between one-sided and two-sided limits. All right, so what I showed you earlier would have been called a two-sided limit. So I'll explain this here. So again, this new marker. So again, this notation we saw earlier. Limit as x approaches, just plain old a of some function equals, say L. All right, this is referred to as, we didn't call it this earlier, but they are going to now. This is a two-sided limit. All right, and so in the graph, what this means, graphically, and we saw this earlier, is that as x approaches a, y will approach L or become L, but there's this point, a comma L, and the graph of our function with this notation approaches that location on both sides. All right, so here's y equals, f of x. The graph approaches that location, that point, on both sides. So then you have what we're going to be introduced to here in these objectives, one-sided limits. All right, that's a two-sided, one-sided limits. Now there are 2 of these. Okay, one of them is your left-sided limits. And the notation for this is you got the limit as the value of x, or whatever your input variable is called, approaches a. Now, to indicate they want you to just approach A from the left, you're going to see a little minus sign here. So it looks like A to the minus power, the negative sign power, but that little negative sign means that you'd only be plugging in values of x smaller than A, all right, to the left of A. And then the rest of the notation is the same. Right? That's the only difference, this little minus sign. So if I say this, the limit as x approaches A from the left or from below, plugging in values less than A, getting closer and closer to A, of f of x equals L, graphically, that means this. So again, you have this value called A on the x-axis that we're approaching, but from the left side only. And then they're saying this, the output is approaching some value called L. So again, here's the point, empty point, doesn't have to be there, A comma L. So our graph is this is only telling me that the graph of our function approaches that point on the left side. All right, so from the left of A, that location is being approached with this y value of L. On the right side, don't care. When you see this little minus notation, you don't even have to worry about what's happening to the right of A. This is simply asking you what happens when x is less than A, approaching A, right? So to the left of A. And then you have, we squeeze this in here, right-sided limits. So the notation is the limit as x approaches A, but then instead of a little minus above the A, you see this little plus sign above the A. So all that means is that when you plug in values, if you want to make a table or look at a graph and see what's happening to some function, this is plugging in values, greater than A. Right? That's greater than A or to the right of A on the x-axis. And the rest of the notation doesn't change. Right? You got of f of some function equals, some limit. Now graphically, that would mean the following. The value we're approaching is A, but from the right side only, right? The little plus will indicate I'm plugging in values, to the right of A and getting nearer and nearer to A. And this is saying the output's approaching this L value, right? So once again, here's the point, A comma L. I'm keeping it empty. It doesn't have to be there. It could be there. It could be solid, but it doesn't have to be there for a limit to exist. All this is saying graphically is that the graph of our function is approaching that location. So here's y equals f of x. The graph of our function is approaching that location, this AL point, but only from the right side. So if you see this little plus notation, you only have to worry about what's happening on the right side of the input, of the value A. Now, the relationship between one-sided limits and our two-sided limit is if the left side limit exists and the right side limit exists and they are the same value, then we have a two-sided limit existing. And this is actually an if and only if statement, goes in both directions. So I'll put that up here. So the relationship between these is the limit as x approaches A, right? So just without the little plus or minus, right? So the two-sided limit of a function is L, if and only if. This is if, you'll see this if sometimes. This means it goes both directions. If this, then this, and then if this, then that. The left side limit, so the limit as x approaches A from the left of the function is L, and at the same time, the right side of the limit is also L. So limit as x approaches a with the little plus sign is equal to L. So again, graphically, here's this point A comma L. So yeah, so let's say this side here. If both of these are true, so the left side of the graph, if you look at the left side of to the left of A, the graph is approaching that location, and at the same time, the right side, right, with the plus, is also approaching that location. Well, if both of those are happening, then we can say that the two-sided limit exists and is also L. Now, if either of these were different, right, you'd have a picture like I had up earlier. So like this picture here, see how the left-sided limit would be, say, M, and the right side would be L, and L is not equal to M here. The left side of A approaching one location, the right side of A approaching a totally different location. So then they say again, the two-sided limit exists. So left side limit exists and is this M value. The right-sided limit exists and is this L value, but the two-sided limit doesn't exist because again, they're not going to the same location. Okay. So having noted all of this, so we're given a graph, right, of some function called f, y equals f of x. It says use the graph of f of x to shown below to determine each of the following limits. If any of the limits does not exist, you're entering that circle with the slash symbol, that empty set symbol is your answer. So look at this graph here, and all sorts of points and empty points and jumps and so we got 3 ones to fill in, and they're all x approaching 4, but from different sides. Some one-sided limits and then the two-sided limit. All right, so look, as x approaches 4, with the little minus here means from the left. So here's x equals 4. Right, hopefully, again, you can see my cursor. So as x approaches 4, from the left, look to the left of 4, the graph is going toward this empty point down here with a y value of -5. Right, so to the left of 4, the location that's being approached is 4, -5. So we'd say the left side limit was -5. And the y coordinate of the location you're approaching. All right, well then this next one is the limit as x approaches 4 with the little plus sign above it. So that means from the right side of 4. So go back up here and look to the right of 4. And on that part of the graph, as I move, toward 4, see how the graph is approaching this solid point that has a y value of 1, 0.41. So my right-sided limit is 1. All right, the limit as x approaches 4 from the right is +1. And based on what I was saying on my previous page, handwritten page, see how these are different, right? The left side's approaching a y value of -5. The right side is approaching a y value of 1. Since these are not the same location, right, clearly from the picture, the graph is not approaching the same location. It's approaching 2 different locations on both sides of 4. So then the two-sided limit does not exist. So I'm entering that circle with the slash, that empty set symbol there for the two-sided limit, right? The one without the little plus or minus. Great. All right. Again, read through the explanations. All right, so here's just a one-sided limit from a table or a graph. So this is another graphical one. Use the graph of f shown below to determine the following limits. So all sorts of points and missing points and jumps and whatnot here. So just a couple of them. We got a left side limit at 2 and a right side limit at 2. So the first one's, what's the limit as x approaches 2 from the left, right? You got the little minus sign of this function. So here's x equals 2. Again, what happens? Now, I don't care about this solid point above 2 here. Right? I don't care what happens at 2. We want to know what happens to the left of 2, or what location is being approached. Same thing to the right, for the little limit, the second part of the question. But as x approaches 2 from the left, you see that we're approaching this location with the empty point here that has a y value of -2. So we'd say the left side limit as x approaches as x approaches 2 from the left of this function is -2. So I'm putting that there. And it's the same for the right. The limit as x approaches 2 from the right, you get the little plus sign there, is also the same. See how on the right side of 2, the graph is approaching that same location with a y value of -2. So I'm putting -2 there as well. And they don't have it here, but if they had the two-sided limit, right, just the limit as x approaches 2 without the little plus or minus, since these are the same, right, you're approaching the same location on both sides of 2, then they'd say the two-sided limit also existed and was -2. But they don't ask that here. Cool. All right, moving on. All right, so this is from a table now. So you're given a piecewise defined function, and they want the left and right limits used that they're asking for down here using the table below. So the first one is, what's the limit as x approaches -2 from the left? So that means I'm plugging in values of x less than -2, right? So like you see, that's this part of the table, the left half with the x equals -2.1, then -2.01, -2.001, and so on. So you see how as the values of x get closer and closer to -2 on the left side, we'd be plugging into that top piece because that's where x values are less than -2. So that's why they got the -4x squared plus x here. Plugging these values into that top expression. See how the outputs going from -19.74 to -19 point, or -18.71704 and so on. Then when x is, -2.00001, the output is -18.001. That's, you can see the pattern here. We're getting closer and closer and closer to having an output of -18. So I'm going to say that this left side limit is -18. Now I'll go to a graph after this too. I'll show you how to graph piecewise defined functions in Desmos. All right, so then this other limit is, what's the limit as x approaches -2, and then you got the little plus sign, right? So -2 from the right. That means I'm plugging in values bigger than -2. So -1.9, -1.99, that's the right half of this table, -1.999. Now I'm getting closer and closer to being -2 without actually being -2. And you see the outputs here. Now notice they got the -3x squared. That's the bottom piece of this function, the bottom output. That's because, you're plugging things into that when x is greater than or equal to -2, and all these values are greater than -2. So those outputs are -10.83, -11.88, -11.9, -11.99, -11.999, right? Hopefully you can see and guess that the limit here is -12, right? It looks as though the outputs are approaching a value of -12, right? So that's what I'm put in that box. All right, so I'm going to submit this in a second. And I do want to show you how to graph on, piecewise functions in Desmos. This was from quite a bit ago. Right? So f of x equals. So here's how you graph, or one way to graph. I've seen multiple ways, but here's one way I like. So you put the expression for the first piece or one of the pieces in parentheses. So I got, negative 4x squared plus x. And then next to that, in braces, right, so little curly braces there. So it's almost like they're multiplied together even though one's in curly braces. You put the condition, this inequality, x is less than negative 2. So x is less than negative 2. And close curly braces. So what you're going to see here is the part of that graph, you see how it's only the part of the graph up until x equals negative 2, right? It doesn't go beyond negative 2 here. Right, here's negative 2. And if I were to scroll down a bit, you see how it doesn't go beyond x equals negative 2, just this blue graph down here. All right, so then add to that, right, plus, and then I put the next piece, which was in parentheses negative 3x squared, negative 3x squared, and then times in curly braces the inequality for the conditions of that second piece. Right, so that was all. You were only plugging in that output when x is greater than or equal to negative 2. So in the braces here, x is greater than or equal to negative 2. All right. Oh, oh, sorry. I should have put that on a separate line, not plus. Let me just copy and paste that. My apologies. My apologies. It was a different thing I was thinking of. Different site. So I'm gonna just copy and paste this down here. So I'll just do y equals. Okay, so there's the other piece of it. All right, so I got two pieces, one in blue, one in green, and hopefully you can see that they are definitely approaching two different locations to the left and right of negative 2, right? This is approaching the location, we said here's the point negative 2 comma, negative 18 was the left limit right there. There it is there. And I'll make it an open point because it technically shouldn't be there. All right, and label it. But you see how the graph on the left side of negative 2 is approaching that point with the y value of negative 18. And then the other one was, negative 2, negative 12. Again, I'll make this like an open point. Go to settings here. Label it. But yeah, so see that, as I approach negative 2 from the right, the graph is approaching this location, the y value of negative 12. So my two limits there, from the table seem like they're correct. Right, if I go graphical. Now I'm not going to do this for every single one. Most of the time you can just tell from the table if they're giving you a table here. How I just said negative 18 from the left, negative 12 from the right, without really graphing anything. All right, good. All right, so once again, another piecewise defined function. Y equals x when x is less than 3, and 12 times x when x is greater than or equal to 3. And they want what's the limit as x approaches 3 from the left, as x approaches 3 from the right, and then 3 from both sides, right? Now they got the two-sided limit in here. All right, so 3 from the left. So that's plugging in values less than 3. So that's this part of the table with the 2.9, 2.99, 2.0, getting closer and closer to 3. And you see the output is 2.9, 2.99, 2.999, 2.999, right? Getting closer and closer to 3. I hope that's obvious, right? As x approaches 3, on that piece, your output is just x. So x would approach 3, right? So your limit's 3 on that one. Now, as x approaches 3 from the right, right? So that's this part of the table. You're plugging in values of 3, greater than 3, but getting closer and closer to 3. So 3.1, 3.01, 3.001, 3.00001, right? And look at the outputs. Now you're plugging into 12 times x though, because again you're plugging in values greater than 3. And there's 37.2, 36.12, 36.012, I'm hoping it's obvious looking at these that the output is approaching, getting closer to 36. So that's what I'm putting for that. Now, this left side limit was 3, the right side limit was 36. Since these are not the same location, not the same value, the two-sided limit does not exist, and I'm entering that empty set symbol like they asked for. Right? Okay, you can read through the explanations whenever you get a chance. This is from a graph again. So again, picture some function called f. What's just the left side and right side limit at 2. So as x approaches 2 from the left, so as I approach 2, so I'm on this piece of the graph, and I'm approaching this open point here with a y value of 0. And same thing for the right side. You see on the right side of x equals 2, you approach 2 from the right side, you're also approaching that same location with a y value of 0. So both of these are 0. Left side approaching y equals 0, right side of 2 approaching y equals 0. And that's it. Now, if they had the two-sided limit there, if they had just limit as x approaches 2 of f of x, that would also be 0, because it's the same thing on both sides. All right, from a table once more. All right, so as x approaches 3 from the left, so that's these values, less than 3, negative 3.1 to negative 3.00001. So as you get closer and closer to negative 3 from the left, you see the output is getting closer and closer to negative 10. All right, I hope that's obvious, that it's getting closer to negative 10. So that's my left side limit. And then as x approaches negative 3 from the right, so I'm plugging in values bigger than negative 3 and getting closer and closer to negative 3. So that's this part of the table with negative 2.9, negative 2.99, all the way down to negative 2.99999. And look at the outputs. Negative 25.23, all the way to, when we get closer to negative 3, the output is negative 26.9998. So it's looking as though the output is approaching negative 27, right? It's getting really close to negative 27, so that's my limit. And again, you can make a graph like I did earlier and see the locations that they're approaching, but I'm hoping it's obvious from the tables. Great. And if they had the two-sided limit there, it would not exist, right? It's going to one location on the left and a totally different location on the right. All right, so another one of these tables with a piecewise defined function. All right, so as x approaches 2 from the left, that's this part of the table. And I'm hoping it's obvious that the outputs are approaching negative 16, right? So my left side limit looks like negative 16. As x approaches negative 2 from the right, right? That's this part of the table, where the values of x are bigger than negative 2, to the right of negative 2, getting closer to negative 2. Looks like the outputs are approaching negative 6, right? You got negative 5.99998. That's really, the limit looks like, I would guess it was negative 6 from all that. And once again, left side limit, negative 16, right side limit, negative 6. Clearly different values, so the graph would be approaching two different locations around negative 2. So the two-sided limit, once again, does not exist. Little empty set symbol. All right, so another graphical one. So here it's negative 4. So as x approaches negative 4, so here's negative 4 on the x-axis. From the left side, we're approaching this open point, which has a y value of negative 1, right? So the left side limit is negative 1. And then the right side limit, right to the right of negative 4, the graph, now you're approaching this solid point location with a y value of positive 1. So the right side limit is positive 1. And then once again, like some other problems earlier, the left side limit, negative 1, right side limit, positive 1, right? So the two-sided limit doesn't exist. They're not approaching the same exact location. So again, the empty set symbol here. Hooray. All right, so only two more objectives left that are related to infinite limits. Let's see the last two here, infinite limits. So I put up a picture like where one of these is going to happen earlier, and I'll explain infinite limits more in a second here. But this right here, I had this picture up earlier. If you're approaching A, either from the left or from the right, and the output is getting larger forever, right, going to infinity, or going down forever, getting larger negative forever, then they'll say you have an infinite limit. All right, so let me explain that some more. Draw the different scenarios up here. So infinite limits. So this is so you can have a left side. So when they say the limit as x approaches a, from the left of some function is, positive infinity or just infinity. Usually the plus isn't there if it's just positive infinity. What that means graphically. So again, you got this x approaching a from the left side. Now, if you're approaching positive infinity, again, I'm going to put a little dotted line here at a, vertical line. What this means is that to the left side of a, the graph, the outputs are going up forever, getting larger and larger and larger. So the closer x gets to a, the larger the output gets. And in either of these cases where we have an infinite limit, the vertical line x equals a, right, this dotted line I put in here, will be called a vertical asymptote. All right, so this comes up on occasion. All right, so I could have the left side limit approach positive infinity. I could have the left side limit of some function approach negative infinity. So if you see this, it means the following graphically. And here's x equals a. Gonna make a little, again, vertical dotted line here. So yeah, this means that from the left side of a, the outputs are going to, negative infinity. So the closer to a I get from the left, the outputs are getting larger and larger negative. Still, they would call x equals a vertical asymptote. Again, that's the case in any of these infinite limit scenarios. All right, so I'll just put up all this. I'll just put up all the stuff. All right, so another version. Now those were left side limits. I could do the right side limits as well, being infinite. So if I approach a, little plus sign here from the right, and I'm getting positive infinity, so it's not a number, right? Infinity is not a number. So you could still say that the limit doesn't exist, but they're going to have you put in infinity or negative infinity just to indicate which direction the graph is going in, as you approach a. So again, here's a little dotted line, vertical line, and then this is telling me that the graph of my function, as I get closer to a, the graph is going higher and higher forever, right? The outputs are getting larger and larger, going to infinity. Then I can have the limit as x approaches a from the right once more of a function is negative infinity, just means, to the right side of a. So here's a again, a little dotted vertical line. Again, this just means that to the right of a, as I get closer and closer to x equals a, the outputs are going down forever. Right. And then, of course, if you have a two-sided limit, that's infinite. That means both sides are doing the same thing. Both sides are going in the same direction. So there's a two-sided limit that's infinite. So if you got if the two-sided limit is infinite, positive infinity. So what that means is that, graphically, in a little dotted vertical line, it means on both sides, to the left of a, to the right of a, both go into positive infinity, right? So your part of the graph would look like that. And then if a two-sided limit was, infinite but in the negative direction, it's just the other way around, right? So A, little vertical, asymptote dotted line there. So yeah, this means on both sides, the graph is going down forever, right? Has getting larger and larger negative. So the part of the graph would look like this around x equals a. Now, the only time you're going to actually say dn does not exist for these is when the left side and right side are different infinities. So when the left side and right side limits are, different infinities, then we're going to say, limit does not exist. So in those cases, so you got here's x equals a. So if a graph did this, say to the left went to positive infinity and then to the right went to negative infinity, then we're going to say the limit as x approaches a dne, right? Also the other way around. If this is going down and this is going up forever, again, you'll say the two-sided limit doesn't exist, right? So the left side limit positive infinity, the right side limit negative infinity, or right, and here's a, or the left side limit is negative infinity and the right side limit is positive infinity. Either way, if they're different, we're going to say the two-sided limit doesn't exist, just like usual, right? If the left side limit and right side limit aren't the same, the two-sided limit does not exist. All right, so the graphical interpretation of limits. And of course, with a table, when you're plugging in values, you're just going to see bigger and bigger numbers, either positively or negatively. And that, should indicate on a table what your limit is if your limit is infinite. So like here with the tables. So we're given this function, right, f of x equals negative, 3 over x minus 8. Here's a table, and you see that, as x approaches 8 from the left, so that's I'm plugging in values less than 8, so that's this left half of the table with 7.9, 7.99, all the way down to 7.99999. That's really, really close to 8, but on the left. See how the outputs are getting larger and larger and are positive? So yeah, they want me to put, infinity here, you can put positive infinity. Now for positive infinity, you can just put infinity. That's implied to be positive. And then as x approaches 8 from the right side, the little plus sign, it means I'm plugging in values greater than 8, but getting closer and closer to 8. So that's this 8.1 down to 8.00001. And hopefully you're seeing that the outputs are getting larger and larger, but negative, right? So it looks like from the table, the limit from the right side of 8 is, now here's where I got to put the minus, negative infinity. And the infinity symbol is down here on the keyboard. And like I was saying on the last page, the handwritten page, if the left side limit and right side limit are different kinds of infinity, right? The left side limit positive infinity, the right side limit's negative infinity, then the two-sided limit is non-existent, right? DNE, and then they want that empty set symbol. Now I'll go to the graphs for this one, all right, just for this first one here. So back to graphing. Back at Desmos, here's, the function we were given, f of x equals, it was -3 over x minus 8. And I'll even put up, here, I'll put up x equals 8 and make it like a dotted line, right? One of those vertical asymptotes. So like that. So hopefully you can see from the picture, that is, I approach 8 from the left, the output's going up forever, right? So we got a positive infinite limit to the left of 8. And then as I approach 8 from the right, it's going down forever, right? The outputs are approaching negative infinity. And so, different infinities on either side. So then the two-sided, again, does not exist. So you can look at a graph to help you too. So this is just simply now, so this is like a problem earlier where you're just filling in pieces of the notation. So write the following, just fill in the pieces of this notation for the following limit. So they say the function f of x equals negative, 3 over x plus 2 squared decreases without bound as the values of x approach negative 2. So notice it didn't say from the left or from the right. It just says as x approaches negative 2. So that's going in this box here after the arrow. The limit as x approaches negative 2 of the expression we'd be plugging our values in goes in after this limit here. And so negative 3 over the quantity x plus 2 squared. And then it said decreases without bound. So going down, decreasing forever. So that's a negative infinity limit. And you can verify this by looking at a graph, making a table. All right, so that was, I'll show you here. So the function we were given was negative 3 over x plus 2 squared. And then so I'll put in x equals negative 2 like they had. They talked about x equals negative 2, maybe make it a dashed line. Right, so hopefully you can see from the picture here that on the left side of negative 2, going down forever. On the right side of negative 2, going down forever. So the two-sided limit, right, as x approaches negative 2 for this particular function, that the limit is negative infinity, as I stated in all this. Right, so again, it's just really filling in the pieces of the notation based on what they described. Right, so I already talked about vertical asymptotes, right? So vertical asymptote, if the left side limit or the right side limit is some kind of infinity, then you have a vertical asymptote at x equals a. Right? So we just have to, evaluate, they're asking us to evaluate these limits, and then the function will have a vertical asymptote at. Right? Now, quite often, it would make sense to simplify a function. So I'll explain that to you here. We'll do that with this problem. So the function I'm given in this problem is f of x equals, we have negative 4 times the quantity x minus 3 in the numerator divided by, and then you got x plus 3 to the 4th power times x squared minus 9 in the denominator. Now, hopefully it's obvious that x cannot be equal to negative 3 or positive 3 because, then you'd be dividing by 0. So these are possible, so these are candidates for being a vertical asymptote. That doesn't mean they both will be, okay? And candidates, so, maybe vertical asymptotes. Yeah, quite often with fractions, it makes sense to simplify. So I'm going to factor this stuff completely. Now the numerator is already factored, right? You got negative 4 times x minus 3. Denominator is x plus 3. Now I'm going to wait for the power here because x squared minus 9 factors to x minus 3 times x plus 3. So that would make this x plus 3 to the 5th, right? You have x plus 3 to the 4th. and then another x plus 3. So I have x plus 3 to the fifth down here. And then, I mentioned that x can't be negative 3. So if x is not negative 3, you got something up here divided by something down here that aren't 0. So those will divide to be 1. Right? You can cancel your common factors. So our function actually simplifies to negative 4 divided by x plus 3 to the fifth power. But just make sure you understand that x still can't be negative 3 or positive 3. Right? So now we're asked about the limit as x approaches, negative 3 from the left and from the right. All right, so from the right, from the left, and then once we got these, we can say the two-sided limit if it exists. Now look at the simplified version of this. Now you could go to a table, go to a graph, I'll go to a graph. But if you think about it, just a little bit, when x is approaching negative 3 from the right, that means x is greater than negative 3. So like negative 2.9, negative 2.99. If you add 3 to that, that's a small positive value. So I have negative 4 in the numerator, and then I would have a small positive value. I'll put small plus in the denominator. Sometimes I've referred to this as 0 plus, just some small positive number. But you might recall that when dividing by a small number is the same thing as multiplying by a large number. So this is going to be a large number, and a negative divided by a positive is negative. So negative large. All right, so the left side limit is the right side limit is negative infinity. Now for the left side limit, again, x is approaching negative 3 from the left, means I'm plugging in values less than negative 3, smaller than negative 3, so it's negative 3.1, negative 3.1 right to the left of negative 3 on the number line. Well, if I put in negative 3.1 or negative 3.01 and then add 3, it's still negative, but small. Oh yeah, it's a small positive to the fifth power. So I'd have negative 4 in the numerator, and then some small negative number, small minus or 0 minus, to the fifth power would still be small and negative, right? If it's an odd power, negative to an odd. So I'll get rid of that. So a small negative number raised to an odd power would still be small and negative. Now, if that were an even power, squared, fourth, sixth, then it would be positive again. Right? Anything to an even power is still positive. So this here, we've got a negative numerator, a negative denominator, so this will be a positive number. And again, dividing by a small number is multiplying by a large number. So this will be going to positive infinity. So the right side limit, negative infinity, left side limit, positive infinity. And that means the two-sided limit is non-existent. Right, the different infinities. Now let's look at a graph. All right, let's look at a graph. So I'll actually put in, I'll put in the original point, the original function the way they gave it to me. It was f of x equals, you had negative 4, well, I'll put the numerator in parentheses, negative 4 times the quantity x minus 3, and then divided by, and then we had x plus 3 to the fourth power, multiplied by x squared minus 9. 9. And I'll change the color of this to like red or something. And here's the thing we were doing it around x equals negative 3. Definitely change that color. Don't want red and red again. So make that blue and dotted. All right. So look, from the graph, you can see that the left side limit is positive infinity. And as I approach negative 3 from the right, going down forever. So the right side limit is negative infinity, the left side limit is positive infinity, and therefore the two-side limit doesn't exist. So that's what I'm filling in these boxes here. So again, this is the right side limit, which was negative infinity. This is the left side limit, which is positive infinity or just infinity. And so the two-sided limit, does not exist. All right, now the empty set symbol doesn't show up, but you can find it if you don't see a symbol in your keyboard, you can drop down, go to sets here, and it should be in the empty set, the empty set symbol. It's a set. So that's it does not exist. Now, the function will have a vertical asymptote at x equals -3. I mean, you saw it, right? That's clearly a vertical asymptote, right? Like I said, if either side, right, it doesn't have to be both. If either side of a line, if either side goes to infinity or negative infinity, they call that line a vertical asymptote, right? So either side goes to some kind of infinity. You have a vertical asymptote there. So there is a vertical asymptote at x equals -3. All right, but not at x equals +3. All right, I mentioned x equals +3 was a candidate, but you see how the x minus 3 is canceled here? So now +3 doesn't cause a problem, or it doesn't make me divide by 0. So there'd just be a hole in the graph there. So if you go back and watch, I'll show you there's a hole in the graph at x equals +3. Right, look, I'll move the cursor here. See how there's a 3 comma undefined, right? You still can't plug 3 in. There's just no asymptote there, right? It's just one missing point. All right, so let's submit this. Read through the answer explanations, all that stuff. And I got a graph there. Cool. All right, so this is pretty similar. Now notice how the denominator, the x plus 10, has an even power. So you have 1 in the numerator, and then x plus 10 to an even power. And having x approach -10 from either side won't matter because you're going to have a small positive number in the denominator, right? You'll have a negative. From the left, it'll be negative, but then you got to the 6th power. Raising to an even power makes you positive again. So left side limit, right side limit, both of them, you'll end up with 1 in the numerator and some small positive numbers in the denominator, but that means you're multiplying by large positive numbers. So you have a positive numerator, positive denominator. This is going positive infinity on both sides. So it's infinity on one, infinity on the other, and if it's the same infinity on both sides, then the two-sided is also that infinity, right? You're not going to write D in either. And so x equals -10 is where there's going to be a vertical asymptote here, right? On either side of -10, there's an infinite limit. So x equals -10 would be called a vertical asymptote. Right, and once again, if you wanted to, right, you could go make a graph of this thing. It was f of x, equals 1 over x plus 10 to the 6th power. And if I go to over where -10 is, right, you see how to the left side of -10, I'll put in x equals -10, make an asymptote out of this, dotted line. And you can see the asymptotic behavior, right, going toward that line but not actually touching it. And this is on both sides again. It doesn't have to be on both. As long as it happens on one of the sides, call it an asymptote, right? So you got left side to infinity, right side to infinity, so two-sided to infinity as well, then a vertical asymptote, x equals -10. So this is pretty similar. See how you have the even power down here? So the denominator is going to be positive no matter what, and the numerator is -3. So as x approaches -1 from either side, this will be a negative number, -3 in the numerator, and then some positive small number in the denominator. And again, dividing by a small positive is multiplying by a large positive. So negative times positive will be, so this is negative. So you got negative infinity. This either side of -1 is going to negative infinity. And you can make a graph to verify it, right? That you're going to negative infinity on either side of -1. And since those are both the same infinity, we're going to say the same thing for the two-sided limit. And they don't ask for the vertical asymptote here, so that's all they want is the limits. And then there's your graph, right? So you're going to negative infinity on both sides. Here's just a graph. So look at x equals -6. See, they got this dotted line here at -6. So you see on the left side going up forever. So the left side limits positive infinity. Right side going down forever. So the right side is negative infinity, meaning the two-sided will say does not exist. So left side, positive infinity. The right side limit, negative infinity, and then the empty set symbol does not exist for the two-sided. Right, so almost done. All right, then very similar. This one has an odd power. So like my example on the page earlier, right, where you had something to the fifth power in the denominator, right? That was this one here with the fifth power in the denominator. When there's an odd power, you got to pay a little more attention. So as x approaches -2 from the left, so say -2.1, -2.01, this is going to be a negative number to an odd power, so still negative. So out of a positive divided by a small negative, this is going to negative infinity on the left side. Again, you can make a graph and verify that. On the left side of -2, graph's going down forever. On the right side of -2, so I'm plugging in -1.9, -1.99, but then adding 2 will make it positive small number to the fifth will still be positive. So positive numerator, positive small denominator, the graph's going to positive infinity on the right side of -2. And since these are different infinities, right, we say the two-sided limit doesn't exist. And since at least one of the sides was going to some kind of infinity, they'll say x equals -2 is a vertical asymptote of this function. Right, so I'm hoping you can eventually get to the point where you're doing this quickly. So there's another one very similar to the last one where you got something to an odd power. So a positive numerator, +1, and then something to an odd power. And they're having x approach -3, right? So again, x can't be -3, right? Because you'll be dividing by 0. So it's approaching -3. Now, if x approaches -3 from the left, it means you're plugging in values less than -3, -3.1, -3.01. Adding 3 will give you a small negative number. Raising that to the fifth power will still be negative. So I'd have a positive numerator divided by a small negative number will be a large negative number, okay? So the left side limit is negative infinity. And if you want to look at the graph of this function, look to the left of -3, it's going to go down forever. Right side, everything's positive. So you got to the right side of -3, this will be a positive number in the numerator, +1 divided by a small positive number, which will be a large positive number. So we're going to positive infinity on the right side of -3. Again, you can look at the graph of the function and how it's going up forever to the right of -3. And since these are different infinities, once again, we'll say this two-sided limit does not exist. And because at least one of the sides, was going to infinity, some kind of infinity, they'll say that x equals -3 is a vertical asymptote of this function. Wonderful. All right, cool. All right, so, and hopefully that's a lot of work there, right? That's a pretty long one. A lot of objectives, right? 6 objectives. So I'm hoping that, watching me go through these here helps you when you're working on it on your own. And thank you very much for watching.